So for number 10, the tub of a washer goes into a spin-dry cycle, starting from rest and reaching an angular speed of 5 revolutions per second in 8 seconds. At this point, the person doing laundry opens the lid and a safety switch turns off the washer. The tub slows to rest in 12 seconds. For how many revolutions does the tub turn during this entire 20-second interval? Assume constant angular acceleration while it's starting and stopping. Well, the first thing I want to do is convert this into standard speed. We usually work in radians per second, not revolutions per second. At this point, I hope you're comfortable realizing that each revolution is equal to 2 pi radians. And so 5 revolutions per second becomes simply 10 pi radians per second. Yes, you could convert that to a decimal as well, 31.415 radians per second. But I'm just going to leave it in this format. And now I'm going to show you 2 different ways of solving this one. First of all, graphically, which might be the simplest way. If we create a graph of omega versus time, that is, angular velocity versus time, we actually know at 8 seconds what its angular velocity is and what it is at 0 seconds and at 20. In fact, it's going to look like this. Starts out at 0, gets up to 10 radians per second at 8 seconds, and then by 20 seconds, it's completely stopped. Well, if you have a velocity versus time graph, you know the area underneath gives you displacement. Well, the area underneath an angular velocity versus time graph gives you theta. That's your angular displacement. And so while it's speeding up, we just need to calculate this area. That's just a simple triangle. So while speeding up, the area of that triangle will be 10 pi times 8 times 1/2, which would be 40 pi radians. And then slowing down, we just need to find the area of this portion. That is 12 wide by 10 pi tall times 1/2 gives us 60 pi. That's the total angular displacement, which is the sum of those two, which would be 100 pi. Or dividing, remembering that there's 2 pi radians in each revolution, means that it's going to go through 50 revolutions. And that literally is our answer. Sorry, it's kind of cut off here at the edge. Say you want to solve this one mathematically, how could you do it? Well, there's lots of different ways, but we don't know the angular acceleration. And so I would probably recommend this one. This one has initial velocity, final velocity, time, and displacement, delta x. The rotational equivalent of that would look like this, just translating each of the elements. And if we use that, we can calculate it. While it's speeding up, initial velocity was 0, the final velocity is 10 pi, the time is 8, and you'll discover, oh yeah, 40 pi radians. While it was slowing down, we can use the same equation a second time. Initial velocity is 10 pi, final velocity is 0, time is 12 seconds, and you'll get the 60 pi. Again, just doing a quick little sum of these two, you'll discover the total is 100 pi radians, or again, 50 revolutions. So you can solve this one either mathematically or graphically. In this case, I actually think the graphical representation is probably the easier one, but both work just fine. Good luck.